Today, we are taking on, well, the towering figure of Albert Einstein.
It's hard to think of a bigger figure in science.
Absolutely. He's the undisputed icon of genius, known globally for the wild hair, the cheeky tongue, and of course, the equation E equals mc squared.
But that public image, as powerful as it is, it really obscures a far more fascinating and conflicted reality.
And that's exactly what we want to get into today.
That's our mission. We want to go beyond the pop culture mythology and really treat Einstein as the radical he was.
Oh, radical. I like that framing.
Because that's what he was. We're going to try and understand the actual conceptual earthquake he caused, the shift in thinking that his papers demanded.
But not just the science.
No, not just the science. We also have to address the philosophical battles he fought later in his life and the surprising personal and political struggles that really define the man behind the theory of relativity.
And for this, we have sources that give us some really deep insight into his early isolation, the sheer intellectual audacity it took to formulate relativity, and then his tenacious resistance to the quantum revolution that followed.
And his later role as this global political activist, which is often overlooked.
Exactly.
At the end of the day, it's a study of a relentless idealist. Einstein was driven by this unshakable belief in a simple, beautiful, and crucially an objective reality.
Something that exists independently of us, the observers.
Precisely. And we're going to trace his path from this isolated, struggling patent clerk all the way to a scientific giant who was, in the end, sort of marginalized by the very revolution he helped ignite.
All because he refused to abandon his fundamental convictions.
He just wouldn't let them go.
So to really understand the man who redefined our universe, we have to start at a beginning that was, well, anything but stellar.
Far from it. We're talking about significant financial hardship for the Einstein family when Albert was just a teenager.
And this instability is really key, isn't it?
It's absolutely crucial because it directly led to his early isolation. His father, Hermann Einstein, had tried to run a factory making electrical equipment.
Which was a booming industry at the time.
A booming industry, but his factory. It just failed to be profitable. And this forced the family to leave Munich and relocate to Italy.
But Albert didn't go with them, not right away.
No, he didn't. Hermann decided that 15-year-old Albert should stay behind in Munich to finish his education at the gymnasium.
Can you imagine that, 15 years old, left alone in a city where your family's business just collapsed?
It must have been incredibly lonely. And during that time, he really only showed exceptional talent in mathematics and physics. He clashed bitterly with the rigid discipline and rote learning that was enforced by the German school system.
So what was he feeding his mind during this lonely and, formative period? He clearly wasn't just sticking to the school curriculum.
No, not at all. His intellectual diet was fantastically eclectic. It really shows his dual nature right from the start.
What was he reading?
On one hand, he was devouring these multi-volume popular science books by a writer named Aaron Bernstein.
Okay.
And they covered just the spectacular mechanics of the universe, everything from stars and meteors to earthquakes and lightning storms.
So the big picture stuff.
The big picture. But at the same time, thanks to a kind teacher who was lending him books, he was also absorbing high culture, including Goethe's classic human drama, Hermann and Dorothea.
So already you see this incredible tension, a deep curiosity about the physical universe, but also this intense philosophical interest in human experience and morality.
And his personality, even then, was one of, let's say, inherent challenge to authority.
That comes through very clearly.
Oh, yeah. That challenge was clear in the classroom. There's a wonderful anecdote that sums up his defiance. It wasn't malicious, just inherent.
What happened?
He had a new math teacher. And Einstein, being just intensely curious, would ask the teacher these sincere, deeply penetrating questions that the teacher simply couldn't answer.
Oh, I can see where this is going.
The disruption amused the class greatly, but it also cemented Einstein's reputation as this unsettling force, someone who asked the inconvenient foundational questions.
He also seemed pretty unaware of social norms, which you see a lot with people who have these very intense internal lives.
His social awkwardness was pronounced in his youth. He had zero pretense and absolutely zero filter.
There are a couple of great examples of this in the sources.
There are. First, he openly shared his anti-religious stance with a classmate, who immediately just recoiled in shock and walked away. Albert just had no awareness that this wasn't an acceptable topic of conversation.
And then there's the scat advisor story. That one is just pure youthful tactlessness.
That absolutely is.
Yeah.
He'd read this humorous story about King Frederick the Great. A certain nobleman kept pestering Frederick for the honorary title of Privy Counselor.
Okay.
So to finally be rid of him, Frederick grants him the title Scat Advisor.
I love that.
Einstein recounted this tale, laughing heartily, wiping tears from his eyes, only to realize, far too late, that his conversation partner was the son of an actual privy counselor.
Oh, no.
Yeah. His peer was, as you can imagine, not amused. Einstein just lacked that awareness of social hierarchy. His mind was already on a level where those titles meant absolutely nothing.
And this idealism clashed very sharply with reality after he graduated from the Polytechnic in 1900. We jump from this image of a theoretical student to a pretty desperate man just looking for work.
It was a period of acute suffering for him and professional rejection. He spent nearly 2 years without any permanent employment.
Despite graduating.
Despite graduating, the schools he applied to rejected him again and again. They often favored older candidates who had established networks. He had no contacts, and that rebellious attitude certainly preceded him.
And the sources suggest this difficulty wasn't just, intellectual, it was physical.
It took a devastating physical toll. He recalled later that the hardship was so acute, the sheer necessity of earning a meager living so pressing, that he couldn't afford the mental space to think about any abstract scientific problem for a full year.
Wow.
He was essentially starving. And it was during this time that he contracted a liver disease that would bother him for the rest of his life.
He did manage to find a few short-term teaching positions, but even those just revealed his nonconformist streak.
He did. He briefly taught in a town called Winterthur. And when he had to fill out his paperwork with the registrar, the official asked for his religious affiliation.
A standard quest.
A standard question.
Yeah.
But the registrar was visibly dismayed and uncomfortable when Einstein just insisted on writing none. Even a small administrative box could not contain him.
And yet, amid all this poverty and uncertainty, he publishes his very first paper. What was this early work, Consequences of the Theory of Capillarity, about?
It appeared in the Berlin Annals of Physics in 1901. It was about atoms and the attractive forces between them in liquids dealing with capillarity.
So pretty esoteric stuff.
Very. And what's remarkable is the subject matter. It was so far removed from any immediate practical application, and it dealt with the reality of atoms and forces, a subject that was still highly speculative at the time.
So he was already asserting the reality of things you can't see.
Exactly. He was asserting the reality of subvisible physical entities, a fundamental commitment to realism that would define his entire career.
And this intellectual rigor eventually led to the famous Academy Olympia. It sounds less like a real academy and more of a, smoke-filled, intense philosophical club.
That's exactly what it was. It was a reaction to his desperate attempt to earn some money. He placed an ad offering physics tutoring for the meager price of 3 francs an hour.
How many tapers did he get?
That ad yielded exactly one client, a Romanian student named Maurice Solovin.
So Solovin comes for tutoring, but what he gets instead is a masterclass in philosophical debate.
Indeed. Instead of dry physics lessons, Einstein, Solovin, and eventually another friend, Conrad Habich, just plunged into these endless, exhaustive philosophical debates.
What were they reading?
They studied thinkers who questioned the very basis of scientific knowledge itself. Carl Pearson's Grammar of Science was a favorite.
And what was Pearson's argument?
Pearson argued that scientific laws are really just ways to categorize our sensations, not necessarily descriptions of an objective reality. It's an idea Einstein wrestled with and ultimately rejected, but one that really honed his critical mind.
And their meeting space was legendarily polluted with pipe smoke, much to the dismay of his future wife, Mileva Maric.
Oh, Mileva was concerned for their safety. The small attic room where Albert lived was so thick with smoke from their pipes that she once looked in and genuinely feared the place was on fire.
And all that was left was ash.
The only physical remnant of this intense intellectual exchange, she observed, was this constant accumulation of ash and cigarette butts.
But the perfect crystallization of Einstein's state of mind during this period, his incredible, almost pathological focus, has to be the caviar story.
It is the ultimate anecdote of the focused mind overriding the senses. For his birthday, March 14th, the Academy members pooled their meager resources to surprise him with Russian caviar.
Which was a delicacy he had long wanted to try, a luxurious, rare treat, especially for them.
Oh, absolutely. So he took a spoonful, put it in his mouth, and without pausing, just continued his intense philosophical discussion on Newton's law of inertia and the concept of causality.
So he's eating and talking.
He kept talking, kept arguing, kept eating the caviar until the plate was completely empty.
And he didn't even realize what he'd consumed until they prompted him.
Not at all. When his friends finally asked him if he had enjoyed the caviar, he stopped, looked up, and this sadness just washed over his face. He exclaimed, "How was that caviar?"
Unbelievable.
His profound ability to immerse himself completely in an abstract problem rendered the most intense sensory pleasure utterly irrelevant. And this, more than any equation, defines the state of mind that led to 1905.
That profound focus, honed during those difficult years of the Academy Olympia and the Patent Office, it all culminated in the Annus Mirabilis, the miracle year of 1905. The speed and the quality of his work that year, done while he was processing patent applications, it remains genuinely staggering.
It is truly one of the most productive years in the history of science. In rapid succession, he produced 4 papers that just fundamentally changed physics.
On what subjects?
He addressed the photoelectric effect, which introduced light quanta, Brownian motion, and of course, special relativity. And the relativity paper on the electrodynamics of moving bodies was finished in an astonishingly short 15 weeks.
So let's unpack the problem he was solving. For decades, physics was, well, obsessed with this concept of the ether. Why was the ether so necessary?
The ether was a conceptual necessity that came out of wave theory. Since sound waves need air to travel and water waves need water, physicists reasoned that light waves,
Which were electromagnetic waves according to Maxwell's equation.
exactly, they must need a fixed universal medium to propagate through. They called this the luminiferous ether.
And this ether was supposed to be the one absolute fixed reference frame in the entire universe, the standard of absolute rest.
That was the idea. And if the Earth was moving through this fixed medium, scientists should be able to measure an ether wind.
Which would let them measure the Earth's absolute velocity.
Right, but all the extremely precise experiments that were designed to detect this absolute motion failed.
Famously, Michelson and Morley in 1887.
Right, and later, more subtly, the Troughton and Nobel experiment in 1903, which tried to detect a torque on a charged capacitor moving through the ether. Also, Eichenwald's experiment in Moscow, trying to measure magnetic effects, all yielded null results.
And these null results were a massive crisis for classical physics. Scientists spent years trying to figure out why the Earth seemed to carry the ether along with it, or why objects shrank just enough to cancel out the effect.
And that's where Einstein's genius lay. Instead of concocting these elaborate physical mechanisms to explain away the failure, he took the failure as the fundamental truth.
So if you can't detect it,
it must be because it doesn't exist. His insight was, if we can't detect a privileged state of motion, it must be because the laws of physics are structured to forbid its detection.
This led directly to the 2 core postulates of special relativity, or STR. The first one sounds relatively simple, the principle of relativity.
Yes. The laws of physics are the same for all observers in uniform, unaccelerated motion. This extends Galileo's original principle to include electromagnetism.
Meaning your physics experiment works the same on a stationary train platform or on a smoothly moving train.
Precisely.
But the second postulate is the radical one. The speed of light is constant for all observers, regardless of their own motion or the motion of the light source.
This just contradicts everything we know from classical mechanics, where velocities are additive.
Right.
Think about it. If a star is speeding towards you, logic dictates that its light should approach you faster than if the star were moving away.
But according to Einstein, it doesn't.
It doesn't. The light always hits your eye at the same speed, roughly 300,000 kilometers per second.
Why is that so counterintuitive? Let's use the sound analogy from the sources.
Okay. If you are standing in a field and a supersonic jet flies past, the speed of the sound relative to you depends entirely on the jet's speed. If the jet is moving towards you at half the speed of sound, the sound waves are compressed, the velocity relative to you changes.
But light doesn't do that.
Light doesn't do that. Fizeau's experiment, which measured light speed in moving water, already hinted that light didn't follow these classical rules, but physicists still clung to the ether. Einstein realized you simply had to accept the constancy of light speed as absolute and let the rest of the universe adjust.
And the adjustment was radical. Newtonian concepts of absolute space, absolute time, absolute mass, they were all shattered.
They become variable, or relative, depending on your frame of reference.
The most shocking consequence, and the one that truly changed our view of reality, is the relativity of simultaneity.
That's the one. Two events that happen at the exact same moment for one observer are demonstrably not simultaneous for an observer who is moving relative to the first.
So the famous lightning strike example, it means there is no objective answer to whether those two bolts truly happened at the same time.
There is no privileged truth. If the observer on the platform sees them simultaneously, the observer on the moving train, who has moved toward one strike and away from the other, sees the flashes sequentially, and both of those observations are equally valid.
Time and space are just inextricably linked.
And your measurements of both depend entirely on your state of motion.
Now, it's crucial to distinguish Einstein's conceptual leap from the earlier mathematical work that was done by others, specifically Hendrik Lorentz and Henri Poincaré.
Oh, absolutely.
They had the math, but they missed the revolution.
They absolutely had the mathematics. They derived what we call the Lorentz transformation, the exact formulas that describe how time stretches and space contracts for moving objects, but they were still operating under the assumption of the ether.
So they saw it as a physical effect.
They saw these effects, time dilation and length contraction, as physical effects caused by movement through the ether, like a kind of mechanical stress.
And Einstein's interpretation was completely different.
He derived the same formulas, but without any ether. He showed the effect was reciprocal.
What do you mean by reciprocal?
If I see your moving ship as contracted, you see my platform, which is stationary to you, as contracted. It's purely relative to the frame of reference.
And Lorentz and Poincaré just couldn't make that leap.
They couldn't. They failed to make that step because they couldn't abandon the philosophical comfort of absolute rest. Einstein's conviction in the simplicity and inherent symmetry of the universe, that the laws of physics must be identical everywhere, that's what allowed him to finally sever the ties to the Newtonian past.
So special relativity dealt with constant, uniform motion. The logical next step, which took him another decade, was tackling acceleration and ultimately gravity. This led to the general theory of relativity, or GTR.
Yes, GTR, which was published formally around 1915 and 1916, was fundamentally a new theory of gravitation. And it originated from what Einstein called, around 1907, the most fortunate thought of my life.
Which was the principle of equivalence.
The principle of equivalence.
Can you break that down for us?
It's conceptually beautiful. Imagine you are in an elevator. If that elevator is accelerating rapidly upward in deep space, you feel pressed to the floor.
Okay.
Now, if that elevator is standing still on Earth, under the influence of gravity, you also feel pressed to the floor. The principle of equivalence states that these two situations, acceleration and gravity, are physically indistinguishable.
So gravity is acceleration.
Gravity is acceleration.
And what's the immediate implication of treating gravity that way, particularly for something like light?
Well, if gravity is acceleration, then light, which must behave like any other accelerated body, has to bend in a gravitational field. This was revolutionary.
And it forced him to accept a pretty contradictory idea.
It did. He had to accept that the speed of light, while it's constant locally in a vacuum, is not constant globally. It must decrease under the influence of gravity. This was a heretical idea even for him at the time, but he had to accept it to make the GTR equations work.
And this led directly to the famous description of gravity not as a force, but as the warping of the stage itself, the warping of space-time.
Right. GTR states that massive objects distort the four-dimensional manifold of space-time. And this curvature is what guides the motion of other objects. They're just following the shortest path, the geodesic, through that curved geometry.
What's fascinating and often overlooked is that the source material emphasizes that GTR showed gravity not only curves space, but it also curves time. And that curved time is actually the main driver of motion.
That is the core insight that separates GTR from just a better Newtonian model. Time literally runs slower near massive objects. And the difference in the rate at which time passes at different points in a gravitational field is the dominant factor in explaining orbital mechanics.
So when we talk about the moon orbiting the Earth, we intuitively think of the curve in space. But you're saying the primary mathematical factor dictating its motion is the curvature of time.
Precisely. If you only calculated the effect of space curvature, your results would be close to Newtonian mechanics. But GTR's incredible accuracy comes from including the time component. This allowed GTR to be a more accurate, more objective description of reality.
How so?
Because it describes objects moving relative to each other within this dynamic, curved geometry, moving away from abstract, isolated concepts.
The first major testable prediction that GTR solved was a long-standing mystery concerning the planet Mercury.
Right. Newtonian mechanics had this persistent minor failure. It could not fully account for the slight secular shift, the slow, gradual rotation of Mercury's orbital path around the Sun.
And GTR.
GTR predicted this shift, called the precession of the perihelion. Precisely. This was a massive internal victory for the theory.
The second prediction, the deflection of starlight, is what made him a global figure. This was confirmed during the 1919 eclipse.
The famous expeditions, led by Arthur Eddington and Andrew Crommelin. They measured starlight passing near the Sun during a total eclipse. GTR predicted that the Sun's gravitational curvature would deflect the light by a specific amount.
And their measurements spectacularly confirmed it.
They did. The news just exploded worldwide. This was empirical proof that the universe was structured according to Einstein's non-Euclidean geometry.
That was the moment that launched him. As he observed, suddenly every cab driver was discussing relativity.
It was hysteria. But it's important to note that the scientific verification didn't end there. Further expeditions were needed, and as the sources point out, these later measurements provided some interesting wrinkles.
What kind of wrinkles?
Expeditions in the 20s, 30s, and 40s generally confirmed the deflection effect, but some of those results showed a deviation.
A deviation.
The deflection was averaging 15 to 20% higher than Einstein's formula required.
Which would immediately prompt physicists to ask questions.
Of course. Is this just a margin of error due to systematic measurement issues? Or are we seeing evidence of a new, subtler mechanism, an unknown force, or field adding additional gravitational attraction? The question remains, but it just shows the complexity inherent in verifying these grand theories.
This brings us to the great irony of Einstein's career. The man who tore down Newtonian absolutes became the staunch defender of classical determinism against the new chaos of quantum mechanics.
He spent the latter half of his life wrestling with the consequences of quantum theory. He was the revolutionary who refused to join the next revolution.
His fundamental objection was philosophical.
Completely.
Yeah.
He said he very, very reluctantly wanted to part with strictly enforced causality.
He viewed the probabilistic nature of quantum mechanics with, well, disdain, famously saying, God does not play dice. He found the whole theory silly.
He did. He believed that the ultimate goal of physics was to discover underlying deterministic laws of cause and effect, that physical reality should not hand over the time and direction of fundamental processes to chance, or Zufall as he called it.
So for him, probability was a tool of our ignorance, not a feature of reality itself.
That's it, exactly.
But the irony is that he was directly responsible for kickstarting quantum theory with his work on light quanta.
Absolutely. This is the profound duality of his career. In 1905, in one of his Annus Mirabilis papers, he resurrected the ancient idea that light consisted of discrete particles. He called them light quanta, and they later became photons.
And this was a direct contradiction of 2 centuries of successful wave theory.
A complete contradiction. And his Nobel Prize wasn't even for relativity, it was for this very quantum concept.
Right. His 1921 Nobel was awarded for discovering the law of the photoelectric effect,
which relied entirely on treating light as discrete particles. So he was rewarded for creating the foundation of the very theory he would later spend decades trying to disprove.
This philosophical battle really came to a head in 1935 with the famous thought experiment known as the EPR paradox, co-authored with Boris Podolsky and Nathan Rosen.
Yes, and this wasn't just a technical disagreement. This was a fight over the definition of reality.
Because Einstein was a realist.
Through and through. He believed that physical laws express real phenomena happening in space and time, independent of the observer or the human mind. This put him squarely against philosophical concepts like Mashism,
which asserted that theories are just ways to categorize our sensations.
Right. And Einstein felt that if quantum mechanics was correct, it meant physical reality was fundamentally subjective.
So the EPR paper was designed to show that quantum mechanics must be an incomplete description of reality because it lacked certain elements of physical existence.
Exactly. They devised a thought experiment around entanglement.
Spooky action at a distance.
His famous phrase for it. The idea is that 2 particles are linked, even when separated by vast distances. If you measure a property of particle A, say its position, you instantaneously know the corresponding property of particle B.
And Einstein's issue was with that instantaneous connection.
It was. If measuring A instantly influences B, it violates the concept of locality, that physical influences can't travel faster than the speed of light. the speed limit set by his own special relativity.
So he argued that if B's properties are instantaneously known after measuring A,
Then those properties must have been real and defined all along before the measurement ever took place.
but quantum mechanics says those properties only become defined upon measurement.
Precisely. So Einstein argued, since B clearly possesses a definite coordinate and impulse, and since measuring A couldn't instantly affect B across space, B must have had those physically real properties independent of any observation. Therefore, quantum mechanics, which denies this, must be an incomplete theory. It must be lacking these hidden variables of reality.
He clearly felt the mathematical formulation of the EPR paper kind of obscured the simple, powerful, philosophical point he was making.
He did. He later confessed that the core concept was buried under the mathematics by Podolsky. But the fundamental challenge stood. The universe must be objectively real, and if the current theory suggested reality was uncertain until observed, then the theory was wrong.
It's such a twist of fate that the very entanglement he despised ultimately saved the integrity of his earlier work.
It did. While entanglement is instantaneous, subsequent studies show that it does not allow the instantaneous transmission of information or a usable signal.
And because no information is sent.
The principle of causality and the cosmic speed limit of light, the foundation of special relativity, are miraculously preserved. The universe he sought was saved, but the randomness he hated remained.
And this philosophical conviction fueled his final scientific crusade, the unified field theory.
He spent the last decades of his life in an increasingly isolated pursuit of a single geometrical field theory. He wanted one comprehensive structure that would elegantly link gravity, which is GTR, and electromagnetism, which is Maxwell's theory.
And ideally, it would bypass or negate the need for the probabilistic chaos of quantum concepts.
That was the ultimate goal. He saw this as the only way to achieve a completed system of views. He wanted the mathematical beauty to eliminate the conflict between concepts like ether and matter, and to provide a fully deterministic description of the cosmos.
And this quest, particularly after he moved to Princeton in 1933, saw his work diverge pretty significantly from mainstream physics.
It really did. The mainstream was focused on particle accelerators and quantum field theory. He was off on his own.
Did this divergence affect his status among his peers?
Yes, significantly. While he remained this global scientific superstar in the public imagination, there was hysteria when his draft unified field article was published in 1929 among his younger colleagues. He became scientifically isolated.
He knew they saw him that way.
Oh, yes. He confessed to Leopold Infeld that colleagues viewed him rather as a relic than as a working physicist, solely focused on a problem they considered intractable or just fundamentally flawed.
It's striking how often the image of the universally acclaimed genius contrasts with the intense struggles of the man, particularly his family life.
The contrast is immense. His global fame just exploded after the 1919 eclipse. He wrote with this characteristic honesty that fame made him stupider and stupider. He recognized the huge, often unbridgeable gap between who he actually was and the myth the public projected onto him.
But he maintained a wonderful lack of pretense, even when he was famous. The story of Max Lau meeting him at the Bern Patent Office before he was famous really captures that simplicity.
It's a great story. Max Lau, going straight from the train station to the patent office, sought out Dr. Einstein. He encounters this disheveled youth with ruffled hair and a rumpled blouse, and politely asks him where he might find the famous Dr. Einstein.
And the youth's reply:
The loudest laugh Lau had ever heard, followed by, "I am Dr. Einstein." That unkempt, irreverent youth was the true Albert.
But his relationship with his first wife, Mileva Maric, suffered terribly under the pressure of his growing fame and his own personal flaws.
Their marriage was intensely strained. Mileva struggled deeply with depression, and she was intensely jealous of his success, especially as her own scientific ambitions faded.
And Einstein, meanwhile, was not faithful.
No, he engaged in multiple affairs, which compounded their difficulties. When they finally divorced, though, he demonstrated his sense of financial duty. He assigned the entire Nobel Prize money he received in 1922 to Mileva and their sons.
That Nobel money was critical for her stability, but she later faced tragedy with their younger son.
Yes, the money allowed her to buy apartments in Zurich, but her finances worsened, particularly after their son, Edward, was diagnosed with schizophrenia.
That's devastating.
It was. By 1939, Mileva had to mortgage one of the apartments to pay for Edward's relentless treatment. Einstein was profoundly affected by the illness. He visited Edward regularly, and they would play the piano together, but the disease was relentless and incurable.
He subsequently married his cousin, Elsa Lowenthal, What role did she play in his life?
Elsa became his shield. She was fiercely protective, managing his schedule, his finances, public appearances, allowing him the intellectual space he needed to focus on physics.
He seemed to appreciate that.
He did. While he continued to have complicated relationships outside the marriage, he appreciated her role immensely. He often jokingly referred to himself as her slave, like the time he entered a pipe-smoking wager with her. She provided a kind of gentle domesticity for him.
And his famously simple, unkempt style, the refusal to wear socks, the baggy clothes, that was a conscious choice, wasn't it?
It was a deliberate defense against what he called bourgeois mediocrity. By the time she was internationally famous, he realized he could adopt any style he wished.
I love the quote about the socks.
It's perfect. He said he'd reached the age where, if someone told him he must wear socks, he could simply choose not to. It was a rejection of formality, a way to maintain personal freedom, even under the intense scrutiny of fame. He was satisfied with the image he had created, something like an ancient sage.
And beyond physics, Einstein used his celebrity as a platform for strong political advocacy, particularly for freedom and tolerance.
He was a staunch, vocal anti-fascist and anti-nationalist. His decision to permanently leave Germany in 1933, when Hitler took power, was a profound statement.
He was very clear about why he was leaving.
Extremely. He declared publicly that he would only live in a country that guaranteed three things: political freedom, tolerance, and equality before the law. Specifically, the right to express one's convictions freely, verbally, and in writing. He compared the rise of fascism to a mental illness affecting society.
On a global scale, he advocated for an idea that seems deeply ambitious even today: world government.
He was deeply committed to the idea. He believed that the nuclear age made absolute national sovereignty an existential threat. He argued consistently that the ultimate aim was a global governing body.
And he thought the Soviet Union might even join.
He suggested they might, if they were guaranteed real security and genuine equality within that framework. He warned that concentrating power solely in military or nationalistic hands was a path to total disaster.
Paradoxically, his activism led directly to what he later came to regret: the initiation of the U.S. atomic bomb project.
That is the ultimate political consequence of his fame. After learning in January 1939 that Otto Hahn and Fritz Strassmann had discovered uranium fission.
Meaning a nuclear weapon might be technically possible.
Right. He was convinced by colleagues Leo Szilard and Eugen Wigner that the U.S. had to act before Nazi Germany did.
And he wrote the famous 1939 letter to President Roosevelt.
He provided the authority and the weight for that crucial letter, which jump-started the Manhattan Project. But post-war, he quickly became one of the most vocal critics of the arms race and the U.S. military response.
He lamented the concentration of power and suppression of thought.
He really did. And his condemnation of the political climate in the U.S. post-war was exceptionally strong, particularly regarding McCarthyism.
He wasn't afraid to speak out.
He was fearless in his opposition to Senator Joseph McCarthy. Einstein called McCarthy a dangerous adventurer and compared the hysterical search for communists to the political climate of Germany in 1932. He stated that the suppression of independent thought in the U.S. had driven the country a long way towards establishing a fascist regime.
A very strong statement.
A very strong statement. He deeply believed that scientific creativity requires free thinking and freedom of spirit, founded on modesty and the conviction that no one has the right to impose their ideas on others. It was a direct commentary on the loyalty oaths and the blacklisting of the McCarthy era.
Looking back across this extraordinary life, we see a man just defined by a fierce commitment to truth and objectivity, sometimes ignoring personal costs and even scientific evidence that didn't fit his ideal of a beautiful, deterministic universe.
That relentless commitment to ideal realism is the perfect synthesis. And it brings us back to a paradox that's inherent in his greatest work.
Which is?
Although it is universally known as the theory of relativity, Einstein himself, perhaps semi-jokingly, sometimes called it the theory of absoluteness.
Why absoluteness? Doesn't that contradict the core idea?
Not at all. He wasn't saying everything is arbitrary. He was finding new absolutes. The core meaning of relativity is the independence, the absolute invariance of the fundamental laws of nature from the state of motion to the reference frame.
So he replaced the old absolutes like space and time.
The deeper, more profound absolute, the unchanging nature of the physical laws themselves, like the speed of light.
His entire life was a quest for that clear, objective picture of the world, independent of the human observer or the complexes of sensations he rejected.
He wanted a universe where phenomena were the determined logical consequences of definite physical causes. This philosophical conviction drove his resistance to Machianism, which tied reality to human sensation, and it drove his lifelong battle against the probabilistic chaos inherent in quantum mechanics.
But the twist, as we discussed, is that the very phenomenon he cited as proof of quantum theory's incompleteness entanglement, his spooky action, ended up being the feature that confirmed the absolute nature of his special relativity.
It did. Einstein fought deterministic chaos until the very end, pursuing the unified field theory to eliminate quantum randomness. Yet entanglement, which operates instantaneously, does not violate STR because, crucially, it cannot transmit classical information.
So it upheld the cosmic speed limit he established.
Miraculously, yes.
So his search for an objective reality, independent of the human observer, remains the ultimate scientific ideal, even if that reality contains the fundamental element he refused to accept.
Exactly. The objective universe he sought is real, but it is structured by an inherent randomness that is simply beyond the grasp of classical determinism. Despite his failure to achieve the unified field theory, that persistent, unwavering conviction in a knowable external reality is the most profound legacy of his scientific spirit.
A remarkable journey through the conceptual and personal revolution of Albert Einstein.
Indeed. And for you to take away and mull over. If Einstein, the world's greatest idealist, struggled so fiercely with the fundamental randomness of quantum reality, does that suggest that the human mind, which constantly seeks order, simplicity, and causal chains, is inherently predisposed to miss the deepest, most complex truths of the universe?
Or is that constant seeking, that striving for order, the only path that ever gets us close enough to glimpse the chaos?
Join us and keep your curiosity well fed. Who knows? The next video might be exactly what you didn't know you needed.